Hi, Professor. My name is Lei Han, and today I'm going to talk about my project. It's about the driver injury analysis in freeway rear-end crashes based on the Bayesain network. My name is Lei Han, and so first I will introduce the research motivation, as we know that rear-end crash are notably prevalent and have bring a lot of significant risks in our freeway system. So as we know, the rear-end crash is the most frequent type of crash in the United States, and they have caused much more economic and life losses in recent years. So if we need to diminish their negative effects and impacts, I think it's very critical to in-depth analyze the risk factors linked to these crashes and know exactly their mechanism. So I searched a lot of papers and related articles and I found that now a lot of studies have focused on analyzing their contributing factors and how these contributing factors affect the injury severities in such crashes. But I found there are still some problems. The first one is that now most of these studies only consider the driver with the most serious injuries, and so they ignore the other drivers' injuries and their physical issues. And also, the second problem is that they can only identify the contributing factors like the driver features and or environmental features and how they affect the crash severity. However, they cannot review those factors, the internal causal relationships between those factors. So these two problems will bring a lot of biases and underestimated factors in those crash injury mechanisms. So I think it's necessary to deeply analyze those contributing factors and to both the drivers and to deeply identify or review their internal relationships. So to deal with such problems, I want to do this project by using the powerful inference capabilities of Bayesian networks to do two things. The first thing is to identify the rear-end crash injury severity mechanisms, and then we need to identify those contributing factors and their inner relationships. So I did this project by three steps. The first is to do the data collection and the data processing to build the modeling data, and then I divided it to the train data and the test data. The train data are using to modeling the Bayesian networks, and we can get the optimal BN model, and then I will do the crash injury mechanism analysis based on the Bayesian network, and I also evaluate the prediction performance of those Bayesian network based on the test dataset. So for my first step, I collect the data from the Open Florida crash website, and I collect 2 years data from 9 interstate freeways like the I-4, I-75, and I-95, and they include three types of data, and I use the unique crash report ID to match those three data into the model data, so I can get the crash time, crash severity, and the crash details, and also I can get the involved vehicle features and driver features. And also I do the speed. I calculated the speed difference during the crash, as we know the speed difference is very important to reflect the collision force. So I named the following worker as A and the leading worker as B. So I collect the estimate speed of this of both of the workers and then calculate the speed difference. But as you can see, the the speed the speed was estimated by the police officers, so the speed difference are mainly distributed on some specific values like the 0, 5, 10, or 20 like that. So I do the discretization like this to divide the speed difference to 4 different levels, like the low, like the medium, like high, and another extremely high. So now, after the data processing, I can go the processed data. Now I have a total of more than 15,000 real and crash samples, and now for the following workload, I have the more I have about 2,400 injury and fatalities crashes. And for the leading worker, I have about 2,600 injury or fatalities crashes. So now we have two target variables. They are the A injury and B injury. And also we have 26 prediction variables. They include the temporal features, environment features, road features, and the driving and vehicle informations about the A and B vehicle. So based on the data, we can build the Bayesain network. But before that, we need to do the feature selection. So I use the random forest model to do that, and I built two random forest model for A injury and B injury, and I use the Gini index to rank the variable importance. And as we can see, the last 8 features are the same for both the A injury and B injury. That means these 8 variables may be the not it may not affect to the targets, and they were removed as as not non-important features. So I use the other variables to do the Bayesian network modeling. And during my project, I found that if I directly build the Bayesian neural network, they can generate some unreasonable and wrong relationships between the features. So I introduced the domain knowledge to this structure. As we can see, I divided the features into the common features, A driver features and B driver features, and they will affect each other by based on the picture, and they will all affect the final crash injury outcomes. So based on that, I can build the BM model, and as we can see, if I don't use the domain knowledge, the generated BM model structure has a lot of wrong direction and unreasonable feature relationships, like the as you can see, the A injury will affect the A crash point and the speed difference that's unreasonable. So I use the domain knowledge, and as we can see, if I use that, we can get much better results. The better one has a correct course direction, and they have good and explainable relationships between those variables. And also, I try different fitting methods to do the modeling, and finally I found that the HC-based network have a higher AIC, BIC at the K2 score. So I think the HC based Bayesian network has a better model fitness. So finally, I removed the network nodes that not related to the driver injury, and and the results are perfect, I think. So now, as we can see, the whole network can be divided into two parts. The left part, the green part, is the sub-network for contributing factors to leading driver injury, and the right part, the yellow part, is another sub-network for the following driver injury severities. So as we can use this model structure to do some explanation and to do some analysis. So the first is I calculate the conditional probability of these two drivers injury level, and as we can see, the first one is the following driver injury severity. So it 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 is affected by two factors. The first one is the speed difference. That means a high speed difference would cause large collision force to the following driver, the A driver. So that's the will increase the injury likelihood of the A is the following driver. And also, as we can see, if the leading vehicle is the mid-sized car or the large car, it will cause greater or bigger damage to the following driver. So the A injury probability will also be higher. And as for the leading driver injury severity, as we can see, when the leading car is the mid-size or large car, that their corresponding probability would be lower, because these big cars will protect the drivers from injury, so they have lower injury probability than the small cars. And also, as we can see, the female would be more likely to get hurt than male, even if they drive the same car, they drive same type of cars. And no, and we can also identify the inner relationships between those contributing factors. And as we can see, I chose two key factors. The first one is the A careless. It means the following driver will get careless. And as we can see, this factor would be affected by the car, by the rural or not rural area and the car type. And the result shows that when people are driving in the rural area, they are more likely to be careless, because I think that may be due to that the single landscape in the rural area may more likely to distract the drivers to lose their attention. And also, as we can see, the careless probability of the large car would be much lower, because I think the driver in the heavy car need to pay more attention to drive the big car, so their probability would be much lower. And another issue is for the car type of the B, is the leading car type. So as we can see, it was affected by the age and the gender of the driver. As we can see, if the age of driver is lower than 30, they would be more likely to drive a small car, no matter they are male or female. But for the male older than 30, they show much more interest in driving the large car. As we can see, the large car probability would be higher. So it shows that people would like to drive big cars like the trucks or the buses. And also, finally, test the model prediction performance based on the test dataset, but generally speaking, the overall prediction performance is not so good, because as we can see, the sensitivity is low and the AUC is only 0.6 or 0.56. It's not so high compared to other studies. So, let's do the conclusions. So I think this project has two innovations. The first one is this project comprehensively extract multiple features like the environment, the driver, and the vehicle to identify contribution factors to the drivers, both the leading driver and the following driver. And the second one is that we developed the Bayesain network which can review the inner relationships of the contributing factors, and also we can identify their impacts to the drivers in injury severity outcomes. But as we can see, this project also have some limitations. Like the first one is that the overall prediction performance is not so good, and the second one is that maybe we get some missing we have missing some key factors, like as we can see, if the driver use the seatbelt, they maybe get lower probability of injury, but that key factors are not included in the crash data, so we cannot analyze that. So that's the main limitations of my research. Okay, that's all my presentation. Thank you for your attention, and thank you so much.